Sequences and series. What the heck are they? They're just lists of numbers. Although the biggest question I get is, what the heck is a series? You see the word sequence all the time when you first learn about these things, but every once in a while your teacher will drop in series. It turns out it just means you're adding. So a series of numbers is a list of numbers that have plus signs in between them, and therefore this would actually equal the sum of these things. So 1 plus 2 plus 3, and this one obviously goes to infinity, so that's going to be a really big number, like infinity will be the total sum. But the point is a series of numbers has addition signs in between them, and then sequence is just going to have those commas in there, and pretty much all the same sort of theories and equations and formulas apply to each one, just that one has the addition signs. So first thing we got to talk about is what is arithmetic sequences versus geometric. Now arithmetic ones just involve adding. Arithmetic, I guess maybe that technically means adding and subtracting, but to get from one term to the next, we're going to add a common difference d. So what that means is, if you just, it's really easy to see in practice. If you look at this first sequence here, how to get from 1 to 2? I don't know, I could have multiplied by 2, or I might have added by 1, right? There's two ways to get from 1 to 2. Either add 1 or multiply by 2. But then to get from 2 to 3, I kind of had to add 1, right? And then I have to add 1 to get from 3 to 4, and add 1 to 4 and 5. So it turns out that the way the sequence was made, the rule sort of for this one, is add 1 to one term to get the next term. So we're just going to keep adding 1. So what would be after 5? 6, then 7, then 8. Pretty obvious. This next one, same story. Only it looks like we're adding 3, because it took me 3 to get from 3 to 6. Then you have to add 3 to get from 6 to 9. So that means we'll go 12, 15, 18, etc. This last one, kind of wacky. There's a 0 in there and stuff. We're actually counting backwards though, which is really just subtracting. So our d, or our common difference, would be that we're actually taking away 10 each time. Take away 10 to get from 10 to 0, take away 10 to get from 0 to negative 10, take away 10 again. So go negative 30, negative 40, d equals negative 10 for this one. So negatives are totally fine for common difference. Now geometric sequences, we're multiplying to get from one to the other. And just like the term adding the common difference could really be subtracting too, because adding or subtracting is just adding a negative number. Similarly, if we're doing a geometric sequence, multiplying and dividing are really kind of two halves of the same coin. Dividing by 2 and multiplying by 1/2 are the same thing. So if you look at the second one, to get from 2 to 1, you could say I divided by 2, but you could also say I multiplied by 1/2, and that's what's going on with this one. Multiply by 1/2 to get from 2 to 1, multiply by 1/2 to get down to 1/2, multiply by 1/2 again to get to this. So this one, next term would be 1/8, then 1/16, etc. indefinitely. This one right here, we're going from 1 to 2, 2 to 4, so we're just multiplying by 2. So 16, 32, dot, dot, dot. So if we're multiplying by 2, that's called the common ratio, or r. So in this one, r equals 2, and this one, r equaled 1/2, which is sort of like dividing by 2, same thing. What about this bottom one? Well, once again, we've got a negative r situation. Turns out if you put in a negative number, you'll get sort of alternating signs, plus minus for each term. To get to 1 to negative 3, you have to multiply by negative 3. You multiply by negative 3 again, you get positive 9. Multiply by negative 3 again, you get negative 27. Multiply by 3 again, you get positive 81. I don't mean plus, I just meant positive. And then negative 243. So the point is, alternating plus minus signs, pretty much always going to be a geometric sequence, and your r is a negative number. That's what's causing you to alternate signs. So arithmetic is addition or subtraction. Geometric is multiplication or division. Take a look at some examples. Now this is a frequent type of problem in the book, and maybe on a quiz. They ask you to, they'll just give you a list of numbers and ask you to classify it as either arithmetic, geometric, or neither. Now here's what's really important, is that it's got to either be one or the other or nothing. So even if you came up with some rule like adding 2 each time would get you the first 3 terms, but then it doesn't work for the 4th term they gave you, that breaks it. That means it doesn't work. So let's take a look at what's going on here. So to get from 3 to negative 3/2, I had 2 choices. I either could have subtracted some wacky number, like 4.5, or I could have just multiplied by negative 1/2. And you see how we have the alternating signs? This one's positive, then this one's negative, then this one's positive, then this one's negative. That's a tip-off. It's probably geometric, if anything. But our rule's got to work always. So if to get from 3 to negative 3 halves, I would have had to multiply by negative 1 half. What happens if I multiply negative 3 halves by negative 1 half? I get positive, because the negatives cancel, 3/4. And then multiply that by a half, and I get negative 3/8. Yes, that does work. So that's geometric. And r equals negative 1 half. What about this one right here? Let's see, we got 1 half. Then multiply 1 half. How would I get from 1 half to 2/3? I would like add a 1/6 or something, but that wouldn't work for this next one. It looks like what the pattern here is I'm just adding 1 to the numerator each time. So you'll notice I go 1, 2, 3, 4, and then the bottom is just going 2, 3, 4, 5. It's like 1 ahead of the numerator, but that's not going to be anything because there's nothing. I'm not multiplying. I'm not dividing. I'm doing some weird rule where I add something at the top and I add something at the bottom separately, and it's two different things. So this is neither. Or if you prefer spelling correctly, I think that'll be, oh man, Google it. I don't know how. Oh, NEI. Okay, it really was NEI. Nice. I'm assuming that's correct. Spell check would have popped up. All right, so last one, 3 halves to 1 half. Now, because there's fractions, you might be thinking, hey, I bet this is geometric. But let's take a look. 3 halves and 1 half, I could have just subtracted 1. So there's a common difference. And if I take away 1 from 1 half, I get negative 1 half. Take away 1 again, I get negative 3 halves. So this is actually arithmetic with common difference equals negative 1. And it's pretty well hidden because everything was fractions. But you just got to be on your toes. You got to think to yourself, what's the difference here? And then would subtracting that same number get me this? And then would that same number get me this? And if it works, that's all you can do. All right, recursive versus explicit formulas. This is just kind of a vocab thing, but it's an important piece of vocab because the instructions on your quiz or test will say, find a recursive formula for whatever, or find an explicit formula. So the key is, and sometimes they'll ask you for both. What recursive means is what we were just doing. You take the term before and you add something to it. So if you look at this formula, what this formula means is that t sub n, so any term you want, is going to be the one before it plus 2. So for example, t sub 10 is going to equal t sub 10 minus 1, which would be t sub 9 plus 2. So what we're saying is that the one before plus a number is going to give us the next one. But of course, to find the 9th term, I'd have to know the 8th term. So if somebody asked me, hey, what's the 8th term of this thing? Of the sequence with this rule, tn equals t sub n minus 1 plus 2, I'd have to say, I don't know, what's the 7th? And they'd say, I don't know. Maybe they'll give you the first term. So if they told you the first term was 1, and you're like, okay. So if I want to get the 8th term, I have to come up with all the terms in between. I have to go 1 and add 2 to that, add 2 to that. So you notice I'm counting by 2's. But I wouldn't be able to get the 8th term until I got, let's see, 1, 2, 3, 4, 5, 6, 7. That's the 8th term right there is 15. But to get it, I had to come up with all the other terms before it. The explicit formula is different than that, though. In that one, you can just punch out anything you want. So like in this one, you'll notice that there's no t sub n minus 1. It's just t sub n. So if I wanted to, I could find the 8th term. And they're saying that that's just going to be 3 plus 5 times n. And n is just this little number, right? This n and this n are the same. So if I want to find the 8th term, I just need to put an 8 in for n. And 5 times 8 is 40, so 43. So that's what's so great about the explicit formula. You can just plug in any number you want, the term number, and it'll spit out the term. This works for both arithmetic and geometric. So the one I just did, it turns out was an arithmetic example because we're essentially counting by 5s. In the later videos, when we look at like sigma notation and stuff, I'll talk about more about how to tell geometric from arithmetic. But when you look at an explicit formula, basically if you have an exponent, if you have your n up in an exponent, that's going to be your r, or your geometric ratio. But on this one, is an explicit formula, because if I wanted to find t to the 5th, all I have to do is plug in 5 for n. So it's going to be 5 and then 2 to the n, and n was 5, I just said. So 5 times 32, because 2 to the 5th is 32. And I think that's going to be 160. So super easy. Explicit formulas, great to know. And in the later videos, when we talk about arithmetic sequences and geometric sequences and we get to all those formulas, then those are pretty much always going to be explicit formulas. These recursive ones are a real pain. All right, factorials, what are they? I'm just introducing them right here because every once in a while, some teachers in that same chapter about sequences and stuff, they'll have some factorial notation. And it won't be for arithmetic or geometric sequences. It'll just be for random sequences in general. But what factorials, that's an exclamation point. So 5 exclamation point, the way you would say that is 5 factorial. And what that means is I want you to take 5 and then multiply it by every integer that's smaller than it all the way down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which of course you could evaluate is 20. Let's see, that's 20, that's 6, so 120. I'm a human calculator. Here's something interesting you'd be able to do. If we want to do 7 factorial over 4 factorial, that's 7 times 6 times 5 times 4 times 3 times 2 times 1 would be 7 factorial. Then 4 factorial would be 4 times 3 times 2 times 1. So we could, at this point, figure out what all that stuff up top multiplied together is and get a number. And then we'll do the same thing at the bottom and then divide them on our calculator or something. But one thing that's kind of nice about factorials is you'll notice that 4 factorial starts with 4, so we have 4, 3, 2, 1. We also have a 4, 3, 2, 1 upstairs. Turns out that will cancel that, and we just get 7 times 6 times 5. 6 times 5 is 30, 6 times 7 is 210. So it makes the computation a lot quicker if you just cancel stuff upstairs and downstairs. All right, last one I just want to point out, there's one of those identities. Just like anything raised to the 0 exponent is 1, turns out that 0 factorial equals 1. Why? No clue. I have no idea. That's just kind of a burn that every teacher and book drops in somewhere in this chapter. So 4 factorial over 0 factorial, it looks like undefined, like you would just guess, oh, we're dividing by 0. You can't do that. It's undefined or no solution or something. But really, this is just 4 times 3 times 2 times 1. Sorry, not over 0. Over 0 factorial, which is 1. So that's going to be 12 times 2 is 24. So pretty crazy. For more factorials, check out the factorial video that will be in the permutations and combinations chapter, because that's when you really get into factorials in earnest, is there. All right, so that's it for how to identify your arithmetic versus geometric sequences. In the next videos, we're going to talk about them extensively, all those formulas, how to use them. I'll pretty much do every type of problem anyone has ever been asked about these types of sequences, so stick around for that.